In this problem, given the shear force diagram in the figure below, assume no couples are applied to the beam. What is the magnitude of the uniformly distributed load on the beam in Newton per meter? So to solve this problem, let's say we have a beam here. Let's call these points A, B, C, D, and E, in which there is some changes in the values of the shear. We can solve for the load by considering each segment. Let's say from point A, notice that we have a shear force of negative 4,000 Newton going downwards. Therefore, there must be a load going downward inducing a force of 4,000 Newton to induce a shear force that is negative 4,000 Newton. Going from point A to point B, there is a change in the value of the shear force. From negative 4,000, it becomes 3,700 Newton from negative to positive, which means that there must be an upward force applied to the beam that would change the value from negative 4,000 to 3,700 Newtons. So we have negative 4,000 plus the unknown force X equal to 3,700 Newton. That force is equal to 7,700 Newtons. Now going from B to C, 3,700 Newton decreases to 1,700 Newton. Therefore, there must be a downward force acting at C that is equal to 3,700 minus the downward force, let's call this X, that will equal to 1,700 Newton. And that unknown force is equal to 2,000 Newtons. Going from C to D, and it remains constant. Notice that from point D to point E, 1,700 Newton decreases in a linear fashion, going from 1,700 to negative 3,100 Newton. Therefore, there must be a uniformly distributed load acting on the beam on segment AE. Let's call this load W. Now going from 1,700 minus the uniformly distributed load times the length to get the resultant, this must be equal to the resulting shear force of negative 3,100 Newton, and that uniform distributed load has a value of 1,600 Newton per meter. And that serves as our final answer. This is our load diagram for the beam to produce this specific shear force.